Hello everyone, I am Haiyin Che from Institute of Data Science and Knowledge Engineering, School of Computer Science in Beijing Institute of Technology. In this session, we will talk about the powerful machine learning tool, TensorFlow. In this chapter, we introduced some useful platforms, Spark MLlib and TensorFlow. And in this session, we will discuss about the concept and the mechanism of TensorFlow. TensorFlow is created by the Google Brain team. It is an open source library for numerical computation and large-scale machine learning. TensorFlow bundles together a lot of machine learning and deep learning, also say neural networking models and algorithms, and make them useful by way of a common metaphor. TensorFlow has grown to become one of the most loved and widely adopted machine learning platforms in the world. A tensor is the core data unit of TensorFlow, which is essentially an array of arbitrary dimensions. Available tensor types include constants, variables, tensor placeholders, and sparse tensors. How TensorFlow works? TensorFlow allows developers to create data flow graphs, structures that describe how data moves through a graph or a series of processing nodes. Each node in the graph represents a mathematical operation, and each connection or edge between nodes is a multidimensional data array, or tensor. TensorFlow provides all of these for the programmer by way of the Python language. Python is easy to learn and work with, and provides convenient ways to express how high-level abstractions can be coupled together. Nodes and tensors in TensorFlow are Python objects, and TensorFlow applications are themselves Python applications. It uses Python to provide a convenient front-end API for building applications with the framework, while executing these applications in high-performance C++. The actual math operations, however, are not performed in Python. The libraries of transformation that are available through TensorFlow are written as high-performance C++ libraries. Python just directs traffic between the pieces and provides high-level programming abstractions to hook them together. TensorFlow applications can be run on most any target that is convenient: a local machine, a cluster, in the cloud, iOS and Android devices, CPU or GPUs. If you use Google's own cloud, you can run TensorFlow on Google's custom TensorFlow Processing Unit (TPU) silicon for further acceleration. The resulting models created by TensorFlow, though, can be deployed on most any device, while they will be used to serve prediction. TensorFlow has grown to become one of the most loved and widely adopted machine learning platforms in the world. Let's watch a video to understand more about TensorFlow.
Created by the Google Brain team, TensorFlow is an open-source library for numerical computation and large-scale machine learning. TensorFlow bundles together a slew of machine learning and deep learning models and algorithms and make them useful by way of common metaphor. Google uses machine learning in all of its products to improve the search engine, the translation, image captioning, or the recommendations. To give you a concrete example, Google users can experience a faster and more refined search with artificial intelligence. If the user types a keyword in the search bar, Google provides a recommendation about what could be the next word. Now, TensorFlow is being used by a lot of companies in the industries, and to name a few, first let's start with Airbnb, the leading global online marketplace and hospitality service. The Airbnb engineers and data science team applies machine learning using TensorFlow to classify the images and detect objects at scale, helping to improve the guest experience. And if we talk about the healthcare industry, using TensorFlow, GE Healthcare is training a neural network to identify specific anatomy during the brain MRI exam to help improve speed and reliability. Now, PayPal is using TensorFlow to stay at the cutting edge of fraud detection. Using TensorFlow, deep transfer learning, and generative modeling, PayPal has been able to recognize complex fraud patterns to increase fraud decline accuracy while improving the experience of legitimate users through increased precision in identification. China Mobile is using TensorFlow to improve their success rate of the network element cutovers. China Mobile has created a deep learning system using TensorFlow that can automatically predict the cutover time window, verify log operations, and detect network anomalies. And this has already successfully supported the world's largest relocation of hundreds of millions IoT HSS. Now, let's talk about the TensorFlow feature, what makes it stand out from the other competition. So TensorFlow offers multiple level of abstractions so you can choose the right one for your needs. You can build and train models by using the high-level Keras API, which makes getting started with TensorFlow and machine learning very easy. If you need more flexibility, Eager Execution allows for immediate iteration and intuitive debugging. When you enable eager execution, you will be executing TensorFlow kernels immediately, rather than constructing graphs that will be executed later. Now, it provides a direct path to protection, whether it's on servers, the edge devices, or the web. TensorFlow lets you train and deploy your model easily, no matter what language or the platform you are using. You can build and train the state-of-the-art models without sacrificing speed or performance. TensorFlow gives you the flexibility and the control with features like Keras Functional API and Model Subclassing API for creation of complex topologies. TensorFlow also supports an ecosystem of powerful add-on libraries and models to experiment with. Now, TensorFlow's name directly derived from its core framework. In TensorFlow, all the computation involves tensor. So a tensor is a vector or a matrix of n dimensions that represents all the data type. All the operations are conducted inside a graph, and the graph is set of a computation that takes place successively. Each operation is called an OP node and are connected to each other. TensorFlow allows the developers to create data flow graphs, which are structures that describe how the data move through a graph or a series of processing nodes. Each node in the graph represents a mathematical operation, and each connection or edge between the nodes is a multidimensional data array or tensor. TensorFlow provides all of this for the programmer by way of the Python language. Python is easy to learn and work with and provides convenient ways to express how high-level abstraction can be coupled together. Nodes and the tensor in the TensorFlow are Python objects, and TensorFlow applications are themselves Python applications. Now, the actual math operations, however, are not performed in Python. The libraries of transformation that are available through TensorFlow are written as high-performance C++ binaries. Python just directs the traffic between the pieces and provides high-level programming abstraction to hook them together. Now, building a neural network cannot get any more simpler. Usually, any machine learning or deep learning process has some similar steps, but in this case of TensorFlow, it is so simple. Any typical machine learning lifecycle or any process has some of these steps like collection of data set, then building the model, training the network, evaluating the model, and then predicting the outcome. In case of TensorFlow, most of the time is occupied in the collection of data set. Now, building your model requires only a few lines of code. Training the network is just a single line. Evaluating the network or the model itself is a single line of code, and predicting the model is also a single line of code. Now, training a neural network cannot get any more easier than this. And that is why TensorFlow remains at the top when compared to the other competitors. Now, TensorFlow competes with a slew of other machine learning frameworks like PyTorch, CNTK, and MNNext. These are the three major frameworks that address many of the same needs. Now, PyTorch, in addition to being built in Python and has many other similarities to TensorFlow, The hardware-accelerated components under the hood, a highly interactive development model that allows for designing as-you-go work, and many useful components are already included. Now, PyTorch is generally a better choice for fast development of projects that need to be up and running in a short time, but TensorFlow wins out for larger projects and more complex workflows. CNTK, the Microsoft Cognitive Toolkit, like TensorFlow, uses a graph structure to describe the data flow, but it focuses more on creating deep learning neural networks. CNTK handles many neural network jobs faster and has a broader set of APIs for Python, C++, C#, and Java, but CNTK isn't currently as easy to learn or deploy as TensorFlow. Now talking about Apache MXNet, adopted by Amazon as a premier deep learning framework on AWS, can scale almost linearly across multiple GPUs and multiple machines. It also supports a broad range of languages API like Python, C++, Scala, R, JavaScript, Julia, Perl, and Go. Although its native API aren't as pleasant to work with as TensorFlow, it is also in the market. Now the thing that gives TensorFlow edge over other competitors is the fact that it is open source and has a huge community support that not only provides researchers a way to build new models, but also a platform to interact with others that face some issues. Now, if we talk about a simple program in TensorFlow, so any program basically consists of a construction phase and then an execution phase. The construction phase is where you build a graph, and execution phase is where you need to evaluate the graph and then create a session, then initialize all the variables. So as you can see here in the example of geometric sequencing, it is so easy to execute. And if this is also hard for you, TensorFlow 2.0, the latest release, makes this even easier to code. It has eager execution by default, which makes things so much simpler and easier. So as you can see, with eager execution, our program has just shrunk.
Now let's look at the structure of TensorFlow 2.0. TensorFlow 2.0 focuses on simplicity and ease of use, featuring updates like easy model building with Keras and eager execution, robust model deployment in production on any platform, powerful experimentation for research. The APIs has been packaged together into a comprehensive platform that supports machine learning workflows from training through deployment. Keras, a user-friendly API, stand for machine learning, will be the central high-level API used to build and train models. The Keras API makes it easy to get started with TensorFlow. Importantly, Keras provides several model building API, sequential functional, and subclassing. So you can choose the right level of abstraction for your project. TensorFlow 2.0's implementation contains enhancement, including eager execution for immediate iteration, and intuitive debugging, and TF data for building scalable input pipeline. Let's take a look at the new architecture of TensorFlow 2.0 using a simplified conceptual diagram as shown. Easy model building here is an example workflow. Load your data using TF point data. Training data is read using input pipeline, which are created using TF point data. Feature characteristics, for example, bucketing and feature across, are described using TF point feature column. Convenient input from in-memory data, for example NumPy, is also supported. Build, train, and validate your model with TF point Keras, or use pre-made estimators. Keras integrates tightly with the rest of TensorFlow, so you can access TensorFlow's feature wherever you want. A set of standard package model, for example, linear or logistic regression, gradient-boosted trees, random forest, are also available to use directly, implemented using the TF Point Estimator API. If you are not looking to train a model from scratch, you will soon be able to use transfer learning to train a Keras or estimator model using modules from TensorFlow Hub. Run and debug with eager execution. Then use TF point function for the benefits of graphs. TensorFlow 2.0 runs with eager execution by default for ease of use and smooth debugging. Additionally, the TF point function annotation transparently translates your Python programs into TensorFlow graphs. This process retaining all the advantages of 1.x TensorFlow graph-based execution, performance optimizations, remote executions, and the ability to serialize, export, and deploy easily, while adding the flexibility and ease of use of expressing programs in simple Python. Use distribution strategies for distributed training. For large machine learning training tasks, the Distribution Strategy API makes it easy to distribute and train models on different hardware configurations without changing the model definition. Since TensorFlow provides support for a range of hardware accelerators like CPUs, GPUs, and TPUs, which is a tensor processing unit, you can enable training workloads to be distributed to single-node, multi-accelerator, as well as multi-node, multi-accelerator configuration, including TPU pools. Although this API supports a variety of cluster configurations, templates to deploy training on Kubernetes clusters in on-premise or cloud environment are provided. Export to save model. TensorFlow will standardize unsaved model as an interchange format for TensorFlow serving TensorFlow-let and TensorFlow.js and TensorFlow Hub and more. Robust model deployment in production on any platform, TensorFlow has always provided a direct path to production. Whether it is on servers, edge devices, or the web, TensorFlow lets you train and deploy your model easily, no matter what language or platform you use. In TensorFlow 2.0, compatibility and parity across platforms and components are improved by standardizing exchange format and aligning APIs. Once you have trained and saved your model, you can execute it directly in your application or serve it using one of the deployment library TensorFlow serving. A TensorFlow library allowing models to be served over HTTP, REST, or gRPC protocol buffers. TensorFlow-let. TensorFlow's lightweight solution for mobile and embedded devices provides the capability to deploy models on Android, iOS, and embedded systems like a Raspberry Pi and Edge TPUs. TensorFlow.js, which enable deploying model in JavaScript environments, such as in a web browser or server-side through Node.js. TensorFlow.js also supports defining models in JavaScript and training directly in the web browser using a Keras-like API. TensorFlow also has support for additional languages, some maintained by the broader community, including C, Java, Go, C#, Rust, Julia, R, and other languages. This picture shows typical platform for the general-purpose computation. Machine learning and deep learning and TensorFlow can be used both for machine learning and deep learning. TensorFlow is powerful experimentation for research. TensorFlow makes it easy to take a new idea from concept to code, and from model to publication. TensorFlow 2.0 incorporates a number of features that enables the definition and the training of state-of-the-art models without sacrificing speed or performance. Keras Functional API and Model Subclass API allows for creation of complex topologies, including using residual layers, custom multi-input-output models, and imperatively written forward passes. Custom training logic. Fine-grained control on gradient computation with TF-point gradient tape and TF custom gradient. And for even more flexibility and controls, the low-level TensorFlow API is always available and working in conjunction with the higher-level abstractions for fully customizable logic. TensorFlow 2.0 brings several new additions that allow researchers and advanced users to experiment using rich extensions, like ragged tensors, TensorFlow probabilities, Tensor2 Tensor, and more to be announced. Along with these capabilities, TensorFlow provides eager execution for easy prototyping and debugging, distribution strategy API and autograph to train at scale, and support for TPUs, making TensorFlow 2.0 an easy-to-use, customizable, and highly scalable platform for conducting state-of-the-art machine learning research and translating that research into production pipelines. To manage using TensorFlow, a series experiments were designed, which include Boston housing prediction using linear regression, objection detection, and variational autoencoder. The steps of each experiment showed in the diagram. Boston housing prediction include preparation, import data, data visualization, build the model, train the model, and result visualization. Objection detection included build the environment of TensorFlow on PC, build a computation graph by using TensorFlow, and using computational graph to compute computation. Variational autoencoder include two stages: network construction and solving gradient disappearing problem using VAE, which consists of learn the concept of layers, build a model that encapsulates layers by using the function sequentially, set the loss function, calculate the gradient of the loss function to perform backpropagation to adjust the parameters, and add some noise into the validation set to solve the gradients disappearing problem. All the experiment material, including the manual and the codes, are provided on the MOOC platform, which can help you to do the hands-on. In this session, we learned the concepts and the mechanism of TensorFlow. Thank you for your attention. If you have any question, feel free to contact me.